Okay, let's take a look at number 15, braking distances. To compare the braking distances for two types of tires, a safety engineer conducts 35 braking tests for each type. The mean braking distance for type A is 42 feet. Assume the population standard deviation is 4.7 feet. The mean braking distance for type B is 45 feet. Assume the population standard deviation is 4.3 feet. At alpha equal 0.1, can the engineer support the claim that the mean braking distances are different for the two types of tires? Okay, so let's go ahead and write that claim in terms of the parameters. Now, because we're dealing with two samples, we have two parameters, mu sub 1 and mu sub 2. Okay, so the claim is that the mean braking differences are different. So the claim as a mathematical statement is going to be mu 1 is not equal to mu 2. Okay, because the engineer is claiming that the mean braking distances are different. Okay, because this does not contain the case of equality, this is the alternative, which makes the null equal, mu 1 equal to mu 2. Okay, so let's go ahead and summarize the information because that's going to be easier for us to identify the pieces. Okay, we've got two types of tires, type A, okay, and the sample size was 35. The sample mean for type A was 42 feet, and we're assuming the standard deviation, the population standard deviation, is 4.7. So for type B in the problem, the sample size was also 35. The sample mean was 45, and we're assuming the population standard deviation is 4.3. Okay, so now we're going to need our standardized test statistic. Okay, so the formula for the standardized test statistic when the population standard deviations are assumed to be known is x bar sub 1 minus x bar sub 2 minus mu sub 1 minus mu sub 2 over the square root of sigma squared sub 1 over n1 plus sigma squared sub 2 over n2. Okay, so for the problems that you're going to encounter in your homework, this is pretty much always going to be equal to 0. Okay, because looking back at the hypotheses, an alternative way to think about this is if I went ahead and subtracted mu 2 from both sides of the equation here, I have the statement that the difference between them is equal to 0. Okay, so this would make the corresponding alternative mu 1 minus mu 2 is not equal to 0. Okay, so this was the claim, that the difference is not equal to 0. Okay, so this part here is equal to 0 in our test statistic. Okay, so what I'm going to do is I'm going to go ahead and fill in the pieces for the rest. Okay, so I've got x bar sub 1, I have 42 minus 45 over the square root of 4.7 squared over 35 plus 4.3 squared over 35. Okay, and that whole thing is under the radical. Okay, so it's going to make this a little bit tricky to calculate this. You definitely need to observe the order of operations. Okay, so we have the numerator up here. That's going to be negative 3. Okay, so let's go ahead and calculate the denominator using the calculator. Okay, so I have the square root of 4.7 squared divided by 35 plus 4.3 squared divided by 35. And then bright arrow out of that. If you have an older TI, you would close parentheses there. Okay, so that's the denominator. Now I need to divide the numerator, which is negative 3 in this case, by that denominator. So I can just carry it over. Okay. So I get a standardized test statistic equal to about negative 2.686. So the next thing I want to do is I want to go ahead and find the critical values. Okay, the critical values will come from the standard normal table. Okay, and we need our level of significance. And that's 0.1 from the problem. Now, because it's a two-tailed test, I know I'm going to have two areas of rejection, so I want to divide alpha in half. Okay, so I need to sketch the distribution. And I'm going to shade two areas of rejection with 0.05 amount of area in each tail. Now again, this should be nothing new at this point. Okay, to get the critical value, I can use my inverse normal function. Okay, so doing that real quick, I'm going to do the lower tail and find the upper tail by symmetry. Okay, so that's negative 1.645. So this makes the positive critical value 1.645. Okay, so we see that our standardized test statistic is way out in this rejection region. Okay, so we know we are going to reject the null, the case of equality here, and we are supporting the engineer's claim. So the question is there enough evidence to support the claim? So yes, since we are rejecting the null and the claim is the alternative, we are in support of the engineer's claim. Okay, so to answer the question, there is sufficient evidence to support the engineer's claim. That the mean braking distances are different. Okay, so let's go ahead and get all of the pieces in the calculator. Okay, and we'll also get the p-value from the output. Okay, I could find the p-value quote-unquote by hand by finding the probability of getting a test statistic at least as extreme as the one attained by the sample. Okay, so my p-value by hand, and because it's a two-tailed test, I'd have to double it, would be the probability of getting a z-score less than negative 2.686. Okay, and then you could go ahead and use your normal CDF here, normal CDF function. But I'm going to go ahead and get the p-value directly from the two-sample z-test. Okay, so to get the pieces in the calculator, I want to press stat, right arrow over to test, and I need to scroll down to two-sample z-test. Okay. Now I'll either have the information in two lists, or I'll have the summary statistics. Okay, I have the summary statistics for this problem. Okay, so it's going to ask for the information. A common mistake is to mix up sample 1 and sample 2, so input carefully. Okay, so sigma sub 1 is 4.7, sigma sub 2 is 4.3, x bar sub 1 is 42, with a sample size of 35, x bar sub 2 was 45, with a sample size of 35. Okay, so if you scroll down a little bit further, you'll have the option to change the sense of direction and the alternative. Okay, so this is the two-tailed test, and then I'm going to press calculate. Okay, so the standardized test statistic here is negative, looking for z-star. Z-star is negative 2.786. Now, going back to my calculation by hand, I'm off a little bit, so I must have done something wrong in this calculation. Okay, so let me go ahead and recalculate that. Okay, to see where my mistake might have been made. Okay, so this numerator is -3. And let's go ahead and calculate that denominator again, 4.7 squared. And I'm dividing that by 35. And then I'm adding it to 4.3 squared, divide by 35. And then I'm arrowing out of the radical. Okay, so I want to take -3 and divide that. There we go. Okay, so recalculating that, I do get the same answer. So I must have made some sort of input error in here. Okay, so I apologize for that, so I want to scratch that. Okay, so if you're playing along at home, you are not going crazy. Okay, so that's -2.786. Okay, so going back to the calculator, stat, then tests, and then my two-sample z-test. Okay, I have all the data input, two-tail test, and press calculate. Okay, so I get the standardized test statistic, and then the corresponding p-value, in this case, was 0.00533. So comparing the p-value to our level of significance, it was 0.1. We're definitely going to reject the null because the p-value is less than or equal to 0.10. Now, if for argument's sake my alpha was 0.05, I would still be rejecting the null. Okay, so here I would still reject. If my level of significance was even smaller, if my level of significance was 0.01, my decision would still be to reject. Okay, so the p-value is helpful in giving us the strength of the rejection because sometimes it's the case that you reject at one level of significance and you fail to reject at another. But in this situation, we're rejecting at all common levels of significance. Now, because we rejected the null hypothesis and we're basing this on a sample, it is possible that we've made a mistake. Not intentional, but errors happen. Since the null was rejected, a type 1 error may have occurred. Okay? Okay, so it is possible that we rejected the null when the null is actually true. Last but not least, now I don't ask for this in the lab, but let's take a look at the corresponding confidence interval. Okay, if alpha is equal to 0.1, then we would be finding a 90% confidence interval. Okay, now your book has the formula for the confidence interval for the difference between two means when you're dealing with independent samples. But I'm going to go ahead and get this in the calculator. I don't ask for this in the lab for Chapter 8, but I do want to mention it because it is, again, consistent with our decision. Okay, so I'm going to press on stat, right arrow over to tests, and I want to scroll down to the two-sample z interval. Now notice that it carried over the information from the hypothesis test, which is really nice. But I do want to change my level of significance to 0.9. Okay, so our confidence interval limits represent the difference between the two means. Okay, so it goes from about -4.77 up to -1.23. Okay, so what this is saying is that the second mean is on average a bit greater than the first mean. Okay, and when that happens, our confidence interval limits are negative. Okay, just based on the order of subtraction. But one thing to keep in mind is this interval does not contain 0, which is the case of equality. Okay, remember the key inequality is in the null hypothesis. So if the confidence interval is not covering 0, then we would definitely be ruling in favor of the alternative. Okay, I hope that makes sense, because the confidence interval is actually very helpful in giving a sense of the magnitude of the difference.